Hi all, in this video we are going to see what is effective mass. So we know that the electrons at rest have a mass of 9.1 into 10 raised to minus 31 kg. Then what do you mean by this effective mass? So this effective mass we always expressed in terms of this rest mass of an electron. So we can say that the rest mass of an electron is different from the effective mass. Then what is effective mass? So we know that in a crystal there are so many identical particles are there. So the electrons in a crystal are not completely free because they interact with the periodic potential of the lattice. That means the identical particles or the crystal is made up of different atoms. So an electron in a crystal are interact with the same particles. So we can say that the wave particle motion is not same as that in free space, or in other words we can say that an electron in a crystal are not completely free. So we can't apply the electron mass at rest for a crystal. So in that cases we are using some altered values of mass. So that mass is called as effective mass. That means the mass that it seems to have when interacting with other identical particles in a thermal distribution. So if you are considering a crystal, it consists of different particles. So the electrons in a crystal are interact with each other particles. Due to this interaction, the mass of an electron at rest is different for such crystals, electrons in such crystals. So the mass of an electron in a crystal have altered. We are using some altered values of mass, and that mass is called as effective mass. So we can say that the electron in a crystal are not free but instead interact with the periodic potential of the lattice. So in applying the usual equation of electrodynamics to charge carriers in a solid, we must use altered values of particle mass. We named it effective mass. So we can't apply the usual electrodynamic equation to a charge carriers in solid or to an electrons in solids. So such cases for a crystal or for a solid we are using some altered values of particle mass, and that is called as effective mass. So find the EK relationship for a free electron and relate it to electron mass. So first we are finding the EK relationship for free electrons, and then from that we are going to define what is electron mass. So we know that for EK, energy versus K is the wave vector. So if we are plotting the energy waves versus K relationship, you will always get a shape of parabola. So this for a conduction band, if the energy states are the conduction band as well as the valence band. So if you are plotting the EK relationship for conduction band minima or for valence band maxima, you will get a shape as shown in this slide. That means it look like a parabolic shape. So we can define that. For that we can take the electron momentum. We know that the momentum of an electron is P is equal to mass into velocity, or in other words we can say that it is hk, where h is the Planck's constant. So also we know that energy of an electron half mv square. The energy equation also we are familiar, that is half mv square. So from the equation 1, that is a P equal to mv, from that you can replace v as P by m, so that you put in second equation. So you will get it as half mv square is half P square by half m into P square by m square. So m and m cancel, so remaining is half P square by m. So in first equation itself we said that P is equal to hk. So here P square becomes h square k square. So in that equation we can see that energy is proportional to k square. So if you are drawing the energy versus k relation, you will get a parabolic shape. So always the energy versus EK relationship is in the form of a parabolic shape. That is, the equation is given as E proportional to k square. So we can say that electron energy is parabolic with wave vector k. So the electron mass to find the electron mass, and that is represented as m star. So to find this electron mass, we are finding the second derivative of energy with respect to k. So we can differentiate our energy equation, that is E is equal to h square k square by 2 m twice with k, that is d square e by dk square. So after finding this d square e by dk square, you will get it as h square by m. So we can say that this electron mass is always inversely related to the curvature or second derivative of the ek relationship. So you will get it as d square e by dk square equal to h square by m. From that we are finding what is m. M is nothing but h square by d square e by dk square. So we can say that m is inversely proportional to, or m is proportional to 1 by d square e by dk square. That is, the m is proportional to the second derivative, inversely proportional to the second derivative of the ek relationship, or this d square e by dk square represent the curvature of our ek relationship, or how much it is parabolic, that is represented by this ek relationship. So we can say that the electron mass, that is represented as m star. Here it is represented as m only. Usually the notation is m star. So m star is proportional to 1 by d square e by dk square, or we can say that the electron mass is inversely related to the curvature or the second derivative of the ek relationship. So we can say that the effective mass of an electron, that is represented as mn star, and that is equal to, we can write it as mn star equal to h square by d square e by dk square. So that is the electron mass. So remember that when an electron in a crystal, the crystal electrons are not completely free. They are interact with the periodic potential of the lattice. That means they will be attracted, or they have some forces among the similar particles. So the electron mass at rest we can't directly apply in such cases. So we are using the effective mass of electron, and this effective mass of electron is inversely proportional to the second derivative of the ek relationship. So that's the definition of effective mass of an electron. So we said that most energy bands are close to parabolic at their minima for conduction band or maxima for valence band. So this effective mass m star is represented as h square by d square e by dk square. So that is the effective mass. So we can we said that the electron mass is inversely related to the curvature of the ek relationship. So we can take an example for that. Here we are taking the gallium arsenide. So the gallium arsenide have 3 bands, that means L, gamma and X. The figure shown that the effective band is L, gamma and X for gallium arsenide, and the band gap energy is 1.43 electron volt. So for this we can see that the gamma band have more curvature compared to other bands. Compared to L or X bands, the curvature is more for gamma bands. So we can say that the effective mass is inversely related to the curvature of ek relationship. So if the curvature is more, then the effective mass should be less. So we can say that the m star of gamma should be less than m star of X or L. So that is the ek relationship versus the effective mass. So when the curvature of ek relationship is more, then the effective mass should be less. So we can say that for gallium arsenide, the effective mass of gamma band, that is that's shown in middle, gamma band is less than that of X or L band. At k equal to 0, the ek relationship near the minimum is usually parabolic. We can represent it as E of k is equal to h square k square by 2m star plus Eg, where Eg is the band gap. And in one more point we can say that in a parabolic band, d square e by dk square is constant, so effective mass is constant. So for a parabolic band, d square E by dk square is constant, so effective mass is also constant. So from equation we can say that effective mass equal to h square by d square E by dk square, where h square is Planck constant, it is a constant, and if d square E by dk square is constant, then the effective mass should be constant. There is no other variable term. Next, we can see the effective mass of an electron and holes in different crystals. So we are taking here germanium, silicon and gallium arsenide as our examples. So in table we can see that Mn star is the effective mass of electron and Mb star is the effective mass of holes. And for germanium it is 0.55 M0 and 0.37 M0. And for silicon it is 1.1 M0 and 0.56 M0. And for gallium arsenide we can see that it is 0.067 M0 and 0.48 M0. Then M0 is the free space mass of electron. So we can see that for the free space mass of an electron and effective mass are different. So the free space mass of an electron is the electron at rest mass is called as M0, and when an electron in crystal they interact with different particles, so due to this force or due to this interaction we can't use the rest mass of an electron. So we are using the effective mass of an electron in such cases. And we can say one more point, that the effective mass should be greater than 0 if d square E by dk square is greater than 0, or otherwise if d square E by dk square is less than 0, the effective mass is also less than 0. So we can say that an electron at conduction band minimum has positive effective mass, that means it has positive curvature, and at valence band maximum has negative effective mass because of negative curvature. So we can say that the valence band electrons with negative charge and negative mass move in an electric field in the same direction as holes with positive charge and positive mass. So we can say that the effective mass, and that is the mass of an electron in a crystal, that depend upon the EK relationship, that means the second derivative of EK relationship, that is inversely proportional to the effective mass is inversely proportional to the second derivative of EK relationship, or we can say that if the curvature of EK relationship is more, then the effective mass is less.